Swayam Prabha. Digital India. Educated India.
In this lecture, I solved some problems using principally planar polar coordinates, and one problem is spherical polar coordinates to get you familiar with the ideas of how to use this coordinate system. So, first problem is to give you a visualization of how one transforms between the Cartesian coordinate system and planar polar coordinate systems. The question is, give the planar polar coordinates for a particle whose position in the Cartesian coordinates is given as 1, 2, 4, second one 3, 6, third one -4, -2. In addition, we would also like to express the unit vectors r and phi in terms of at these positions in terms of vectors I and j. So, let us take the first one where we have x equals 2 and y equals 4. First, let me make a general statement that when I am dealing with planar polar coordinates, if there is a point here x and y, the radial coordinate is given by this distance from the origin, which we call r, and the angular displacement is given by this phi. So, you can easily see, if I make the x and y distances, that this red one horizontally is x and this is y, and therefore, I am going to have r is equal to square root of x square plus y square always, and tangent of phi is equal to y over x. Keep in mind, if I go to the other side, that is in the third quadrant, both x and y are less than 0. Therefore, tangent phi is going to come out to be positive again. So, we should also write here, if x is less than 0 and y is also less than 0, then phi is greater than 180 degrees, although tangent phi will come out to be positive. So, let us now solve the first problem where we are given the Cartesian coordinates as x and y, and therefore, r is going to be square root of 2 square plus 4 square, and that is square root of 20, which is 2 root of 5, and phi is going to be tan inverse of 4 over 2, which is tan inverse of 2. How about the unit vectors? So, let me again make this system here, and this is r at a given x y, the unit vector in r direction is going to be this, and perpendicular to it is the unit vector phi. And we have seen in the lectures where we set up these coordinate systems that r is nothing but cosine of phi I plus sine of phi j, which can also be written as x I plus y j over r. And phi unit vector is minus sine of phi I plus cosine of phi j, which can also be written as minus yi plus xj over r. And therefore, when I write for x, y equals 2, 4, the corresponding unit vectors at that position, so I'll again make it, and here is r unit vector, and here is phi unit vector. I have r is equal to 2i plus 4j over, we have already determined what r is, 2 root 5. And similarly, I have phi unit vector is equal to minus 4i plus 2j over 2 root 5. That's part 1. In the second part, we have taken the coordinates to be 3 and 6, right, which is both positive, and now I can directly write that r is going to be square root of x square plus y square, which is square root of 9 plus 36, which is square root of 45, plus phi is going to be tangent inverse of y over x, which is equal to tangent inverse of 2. So phi remains the same as in the previous question, but r changes. R unit vector, let me write it in red, r unit vector is going to be xi plus yj over r, which comes out to be, in this case, to be 3i plus 6j over square root of 45. And phi unit vector is going to be minus yi plus xj over r, which is equal to minus 6i plus 3j over square root of 45. The final question in this is xy is given to be minus 4 and minus 2. So this point is actually in the third quadrant out here, and therefore the distance r is square root 4 square plus 2 square, which is again 2 root of 5. Phi is equal to tan inverse of minus 2 over minus 4, which is tan inverse half, but that's going to give you an angle which is less than 90 degrees. In this case, phi is actually going to be 180 degrees plus tan inverse 1 over 2, because, let me write in the bracket, x is less than 0 and so is y. How about the unit vectors? R unit vector now is going to be in this direction, and phi unit vector in this direction. This is the phi unit vector and r unit vector. This is where now it becomes important that we realize that phi is 180 plus tan inverse 1 over 2. This, if I were to write this as cosine of phi I plus sine of phi j, then this phi being greater than 180 degrees will be important. On the other hand, if I write it directly as xi plus yj over r, then that sign is automatically taken care of, and this would turn out to be minus 4i minus 2j over square root of 5, and phi unit vector is going to be minus y I plus xj over r, and that's going to be 2i plus minus 4j over 2 root 5. You can see that the x component of phi unit vector is in the positive direction and y component is in the negative direction, and for the r vector the x component is in the negative direction and so is the y vector. So we are being all consistent. Next problem is velocity and Cartesian coordinates of a particle at different instances are given below. Express these velocities in planar, polar coordinates. So one velocity which is given is v equals 2I plus 3j at 2 and 3. So let us see what does it mean. It means I am at the coordinate 2 and 3 and the velocity x component is proportional to x and y is also proportional to y. So this direction is actually going to be same as the r unit vector. But let us do it systematically. I just gave you a picture where you can actually make out that it is in the r unit direction, but in general that will not be the case, and that's where the systematics come into the picture. So let us first calculate what the radial component of the velocity is. Radial component is going to be v vector dot r, which is going to be equal to 2I plus 3j, this is the velocity given, dot r unit vector. Since the particle is at 2, 3, it's going to be 2I plus 3j divided by r, which is the square root of 4 plus 9. So this is going to be 4 plus 9 over root 13, which is root 13. So Vr is root 13. How about V phi, the phi component, the tangential component of the velocity? The tangential component is going to be V dot phi unit vector, which is going to be 2I plus 3j dotted with the phi unit vector, which is minus yi plus xj divided by r, and here I can write this as 2I plus 3j dotted with minus 3I plus 2j divided by r, which is the square root of 13. You can already see that this dot product is 0, and therefore v phi comes out to be 0. This is precisely what we suspected earlier. The velocity in this case is radial, and therefore it can be written as v equals root 13 r unit vector. Keep in mind that at this instant the particle is moving in the radial direction, but the radial unit vector keeps on changing as the particle changes position. I emphasize again that r unit vector is xi plus yj over r, and therefore it depends on x and y. It's not a fixed unit vector in space. As the second example of this, let me take v equals minus 2I plus 3j, and that means at this point the particle is moving somewhat like this, as shown in purple color, and Vr, and this is at minus 3 and 2. So even the position is changed. I am taking a position minus 3 and 2, so somewhere here, and the particle is moving at minus 2 and 3j, something like this. So now you see there is an angle between the radial unit vector and the tangential unit vector, and therefore v is going to have both the components. Let us calculate Vr, which is going to be v dot r unit vector, which is minus 2I plus 3j. This is the velocity dot unit vector is going to be minus 3I plus 2j divided by r, which is square root of 9 plus 4. So this comes out to be 2 times 3 is 6, 3 times 2 is 6, 12 over square root of 13. So Vr is this. How about V phi? V phi is going to be V dot phi, which is equal to minus 2I plus 3j times phi unit vector, which is minus yi. So minus yi is going to be minus 2I plus xj, which is minus 3j divided by square root of 13. So this is going to be equal to 4 minus 9, which is minus 5 over root of 13. Alright, so let's go to the next page and write it again. We got Vr is equal to 12 over 13, 12 over square root of 13, and V phi is equal to minus 5 over square root of 13. And the particle is at position minus 3 and 2, minus 3 and 2, somewhere here. At this point, let me again show that the unit vectors, r unit vector is like this, and phi unit vector is perpendicular to this in this direction. What we find is that Vr is in the same direction as the r unit vector, is positive. V phi, however, is negative. This is V phi, and this is how the particle is moving. So I can write the velocity in planar polar coordinates as 12 over root 13 r at this point minus 5 over root 13 phi. At this position, as the positions change, r and phi unit vectors change, right? If the same velocity, same vector, if the same vector v, which is minus 2I plus 3j, was at some other position, Vr and V phi will change. Let me now take the third problem. Express Kepler's second law, which is also known as the law of area of planetary motion, in planar polar coordinates with the sun at the origin. Use this to prove that the tangential acceleration of a planet is 0 and the force of gravitation, which is understood between the sun and the planet, is towards the sun. Okay, so solution. What is Kepler's second law? Kepler's second law says that the planets, when they move around in an orbit with the sun at the origin, the rate of change of or the rate of sweeping area sweep is constant. That means at some instant a planet moves, say, from position 1 to position 2, it sweeps some area in some certain time or unit time. Suppose it sweeps this area shown by shaded black region, and in some other time it goes from position 3 to position 4 in unit time and covers this much area. These two areas covered per unit time are going to be the same. That's Kepler's second law. And let us express this in planar polar coordinates. So how do I express that? You see, this distance here is r, and if I treat this as a triangle in a very small short time, right, this I made for unit time, but let's take a short time and make it exaggerated. So this is the planet orbit, this is r, and in a very short time delta t it comes to this position here. This time is very short, so it covers a very small angle delta phi. If I were to calculate this area of the shaded region, let me drop a perpendicular from here. This becomes the base. Keep in mind the delta phi is very small. This base distance is going to be r delta phi, and therefore to the first order in delta phi, the area delta A is going to be 1/2 of r times r delta phi, which is 1/2 r square delta phi. So this is the expression for area, infinitesimal area in planar polar coordinates. So we learned that, and therefore delta A over delta t with limit delta t going to 0 is going to be dA dt comes out to be 1/2 r square delta phi by delta t, limit delta t going to 0, phi dot. So dA dt is going to be equal to 1/2 r square phi dot. Let me write that here. So dA dt is 1/2 r square phi dot. Now you see why I neglected the second order. If I included the second order here, if I take delta t going to 0, second order is going to vanish, because delta phi delta t divided by delta t is going to be finite, but delta phi will go to 0. So this is the rate of change of area, and what Kepler's second law says, that dA dt is a constant, which means that 1/2 r square phi dot is a constant, and therefore if I take the time derivative of this quantity 1/2 r square phi dot, since this is a constant, it's going to be 0. Let us now take the derivative. It's going to be 1/2 d by dt of r square phi dot plus 1/2 r square d by dt of phi dot, and this is 0, which gives me r dot phi dot plus 1/2 r square phi double dot is equal to 0. If I take r common, I can write this as r, or r by 2 common, 2 r dot phi dot plus r phi double dot is equal to 0, and as long as r is not 0, this immediately implies that r phi double dot plus 2 r dot phi dot is equal to 0. Notice that this is the expression for tangential component of the acceleration. So Kepler's second law is equivalent to tangential acceleration being 0. Let us see it in figures. This is a planet which is going around. This is the sun. Tangential acceleration means acceleration perpendicular to the radius. Okay, keep this in mind. This is a tangential. It's not along the orbit, it's perpendicular to the orbit. So this acceleration is 0, and therefore only acceleration this planet has, I'll show it in red, is going to be in the direction towards the sun, towards the radius. So this immediately shows that the force between the sun and planet is towards the sun. So you see how important Kepler's law is, and when we analyze it in using planar polar coordinates, how immediately it gives us information. I again emphasize, keep in mind the tangential acceleration is not along the orbit but perpendicular to the radius. I have shown it in green here. Okay. Problem number 4. Problem number 4 says a particle moves in a plane with r dot equals 2t meters per second and phi dot equals 1 radian per second. Find 1 RT as a function of time if R0, that is R at time t equal to 0, is 1 meter. So that means it started at 1 meter. And 2, unit vector phi for the particle position obviously as a function of time. And third, at what distance from the origin is the radial acceleration 0. So let us do this. We've been given, so let me just first make this picture which always tells you a lot of things. A particle is moving out, it started at t equal to 0 at some distance, r equal to 0 equals 1 meter. It is not given what phi position was, so we will take some arbitrary phi position which is, let's say, phi 0, and it moves out. Let me make it in red. It moves out at a speed of r dot t equals 2t meters per second. So as time passes, it moves out faster and faster. At the same time, it is moving in the phi direction with a constant angular speed, and therefore the particle will start going out like this. This will be the trajectory. Now what I want to find is 1 r as a function of time, so I am given r dot which is equal to dr by dt is equal to 2t, and therefore r is going to be equal to t square plus some constant, but I am given r0 is equal to 1, which immediately gives me that 1 equals 0 plus c, or c equals 1. So r as a function of time is given as 1 plus t square meters. That's part 1. Part 2 says find unit vector phi as a function of time. Remember again, as the particle is moving, its phi unit vector keeps on changing with its position, and phi unit vector depends only on phi. So let me write this. Phi unit vector at time t is given as minus sine of phi I plus cosine of phi j, and what I have been given is that phi dot is 1 rad per second, so phi t is going to be t plus some phi naught, which was the phi at t equal to 0, and therefore phi unit vector as a function of time is going to be minus sine of phi 0 plus t I plus cosine of phi 0 plus t j. Third part, I want to find the distance at which the radial acceleration is 0. Now recall that radial acceleration is given as r double dot minus r phi dot square. I am given that r dot is 2t, and therefore r double dot is 2, and I can therefore write ar as a function of time is equal to 2 minus r is given as 1 plus t square, which I have already calculated, and phi dot square is 1. So this is given as 1 minus t square meters per second square, and ar t is equal to 0 implies t equals 1 second, and therefore r is equal to 2 meters. That is the answer. So what we have done in this lecture is solve some illustrative problems as to show how planar polar coordinates are to be used. Eventually, we do not use I and j but use these planar polar coordinates directly. Finally, let me do one problem in spherical polar coordinates, and that is, if I take spherical polar coordinates, if you recall from the lecture, what are these? This is x, y and z. So if I am given a point, spherical polar coordinates give me distance r from the origin, then the position of this vector from the z-axis is specified by giving an angle theta, and position in the xy plane of this point is given by this angle phi. The unit vector theta is going to be the direction perpendicular to unit vector r, which is towards the radius, and phi is in the xy plane again. So theta unit vector is given as, if I were to make it again, going down the plane, making an angle theta from the xy plane. So in the xy plane, theta unit vector has a component cosine of theta, then its x component is going to be cosine of phi I plus cosine of theta, y component is going to be sine phi j, and minus sine theta k. Phi unit vector anyway is in the direction, in the plane, just like in the planar polar coordinates, and it's going to be given as minus sine of phi I plus cosine of phi j. And the radial vector, that is this vector, has a component cosine theta in the z direction and sine theta in the xy plane. So sine theta cosine phi I plus sine theta sine phi j plus cosine theta of k. And what I want to do in this problem is find theta unit vector dot and phi unit vector dot. To calculate theta unit vector dot, let me differentiate the expression given here. I'm showing you by taking it. This is going to be d by dt of cosine of theta cosine of phi I. Writing these vectors in terms of Cartesian unit vectors helps, because Cartesian unit vectors are fixed and therefore I don't have to differentiate them with time, plus cosine of theta sine of phi j minus sine of theta k. And let me differentiate them. When I do that, I get theta unit vector dot is equal to, let me write this again, d by dt of cosine of theta cosine of phi I plus cosine of theta sine of phi j minus sine of theta k. This comes out to be minus sine theta cosine phi I theta dot minus cosine theta sine of phi j phi dot minus sine of theta sine of phi j theta dot plus cosine of theta cosine of phi j phi dot minus cosine of theta theta dot k. If I collect all the theta dot terms, this I can write as theta dot with a minus sign, sine theta cosine phi I plus sine theta sine phi j plus cosine theta k minus, let me also collect phi dot terms, minus phi dot in the bracket cosine theta sine phi j cosine theta cosine phi. This one, mistake here, I am correcting it with red, was I. So this is going to be I. So what I get is minus theta dot, and you can recognize this unit vector here. Let me encircle this with green, is nothing but R unit vector. Minus phi dot cosine theta comes out, and sine phi I minus cosine phi j is nothing but minus phi unit vector. So I can write this whole expression as minus theta dot R unit vector plus phi dot cosine theta in the phi direction. Pictorially, if I look at it, this was my theta unit vector. As theta changes, it changes like this, keeping the phi the same. So it moves, it has a component in the minus r direction, and if phi changes, it moves like this. So it has a component in the positive phi direction, and this is what this expression reflects. How about phi unit vector? Phi unit vector is nothing but d by dt of minus sine phi I plus cosine phi j. So this is going to be minus cosine of phi I phi dot minus sine phi j of phi dot, which I can write as minus phi dot cosine of phi I plus sine of phi j. Now I want to bring this in the form of a combination of r unit vector and theta unit vector. So recall again, r unit vector was sine theta cosine phi I plus sine theta sine phi j plus cosine theta k, and theta unit vector was cosine of theta cosine of phi I plus cosine of theta sine phi j minus sine of theta k. Notice if I take sine of theta, multiply this by r unit vector, add to it cosine of theta, theta unit vector, what will I do? First term, this term here, I'll get sine square theta plus cosine square theta, cosine phi comes out common, so this will become cosine phi I, plus second term again will be sine square theta plus cosine square theta, which is 1, and I get sine phi j, and the last term cancels. So therefore, using this I can write phi unit vector dot is equal to minus phi dot cosine phi I plus sine phi j as equal to minus phi dot sine theta r plus cosine theta theta. Notice that now we have written all these in terms of r, theta and phi, and no reference to Cartesian unit vectors.